right, let's go through the second handout. And this is looking at average rate of change and exponential growth and decay. So, all right, first off, what is the average rate of change? It's just the slope of something. It's just, we're used to slope for a linear function. We have y equals mx plus b, and we're used to the slope formula y2 minus y1 over x2 minus x1. But that's actually what this formula is, where you say y is a function of x. And so, how would you find y2? Well, you'd have to plug x2 into your function. So, why use subscripts when you can just use different letters? So instead of having the same letter x and then having subscripts, we call this a and b. And so f of b, for example, let's just look at like this right here. So the average rate of change from x equals -6 to x equals 2. So both of these right here, these are x values. And what we do is we find x equals -6. Okay, here it is. And then we go to our function value at that spot. So right here, this is f of -6, which is the y value, which is 1, right? And in fact, let me just write down what the computation is that we could do if we were to compute this. Oh, that's right, sorry. The order does not matter. What I mean by that is this computation is the same thing as f of a minus f of b divided by a minus b. What matters is the relative order. So you see, if f of b comes first on top, then b comes first on bottom. And if f of a comes first on top, then a comes first on bottom. That's because, going between the two, you basically just multiplied by 1 in a costume where it's -1 on top and bottom. But okay, so I'm looking at f of -6 minus f of 2 over -6 minus 2. And we just figured out this is 1 minus, and make the bottom -8. So we need to figure out what f of 2 is. And that's going to go right there. So f of 2, hey, that's also 1. That's also 1. And so now we know that this is 0, right? So that would be how you compute the average rate of change. And notice this function here, this is not a linear function. It's not a line. But we can still talk about average rate of change. And we could have just sort of looked at these two spots here and ask ourselves, what is the slope between those two spots? And you can see it's a slope of 0. So this has a slope of 0 here. If we continue, then we have x is -2.5, or sorry, not negative, positive 2.5, and then positive 3. So it looks like positive 2.5, maybe it's somewhere around here. Positive 3 is somewhere around here. So we're looking at this slope here. And this is where, instead of trying to compute it, instead of guessing, oh, this is minus 1.5, and this is -4, and blah, 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 just describe it. This is, if you were standing on this curve, what would that feel like? Well, gosh. And we always want to pretend we're going from left to right. So I would be walking on a downhill, and it's a very steep downhill, right? So the word steep, I'm going to replace with big. And the word downhill, I'm going to replace with negative, okay? This slope is a steep negative number. It looks like it's about -6 or something like that. It's a pretty, big negative number. Whereas, so for the first one, we got 0. For the second one, it's a big negative number. How about for this next thing here? And notice, they no longer wrote out AROC, blah, blah, blah. Even though, okay, I should actually finish this out. This is AROC 2.5 up to 7. I look at just the x values. The x values are 2.5 and 7. Sorry, -2.5 and 7. And then I do a slope computation. Y2, Y1, X2, X1, all that stuff. Okay, so what is this? Let's find -2.5. Okay, -2.5. We're looking at somewhere around here, maybe, up to positive 7, somewhere around here, maybe. So what is this slope? Well, if I was to walk along that, it's a slight uphill. It's a shallow uphill. This is a small positive. Okay, small positive, whatever you get it, small positive. Okay. All right, and this last one is 0 and -4.5. So 0 is up here, -4.5 is maybe here. What would it feel like to walk along this? Oh man, that's a steep uphill. That's a big positive. All right, so now we have to order all of these things. And that's what this question is asking for. I never actually read the question out loud because I jumped straight into computing the average rate of change or making sense of the average rate of change. It's just the slope between 2 points. But this is the type of question, I got this from the sample midterm. It might appear in your future. So let's make sense of it. Well, gosh, I guess the most negative is number 2, because that actually was negative. And then you could hit 0, which is number 1. Then you could be a small positive, which is number 3. And then you could be a big positive, which is number 4. So that's how we'd answer that. Okay, so that's the average rate of change. I'm going to briefly just run through all of these, and we'll spend more time on functions and inverses and things in the future. But let's run through it to make sure we're on the same page as far as notation goes. But the main topic of this handout is going to be average rate of change and some exponential functions. But okay, so let's make sense of this. So f of negative 4. So here's x equals negative 4. And f of negative 4 is the y value that the function hits. And that's this y value here. It's 2. So this is 2, right? The closed dot is telling you what you hit. The open dot is saying, hey, you're not actually going to touch this spot, okay? All right, how about f of negative 2? Well, negative 2, I'm looking at x equals negative 2. So I'm looking in this vertical strip here. And there is no closed dot. There's just an open dot. That's because this is undefined. It does not exist. So you could either say UND for undefined, or you could say DNE for does not exist. We'll accept either one. The point is that the function is not defined there. It's, negative 2 is not in the domain. Okay, so now we get to some newer, fancier notation. So this is k inverse of negative 2. So there's two functions here. One is f and one is k. All right, so let's look at k. Whoop. All right, now, here's the deal. This column represents the input, and this column represents the output, and k brings you this way. So in other words, if the problem asked, what is k of 3? Well, I would say 3 is my input, and k will take 3 over to 4. So this will equal 4, okay? Now, when something says k inverse, then it essentially, for a tabular form, it goes this way, okay? So k inverse of negative 2, we imagine starting with negative 2 and going this way, and we find out that it's negative 4, okay? And I guess I have nothing deep to say about that right now, because we'll dive into inverse functions later, but this was negative 4. Part D is just a notation thing. So what this means when this collection of symbols happens, it's shorthand notation for saying f of 1 plus k of 1. And notice it saved us writing like a very small amount in difference, right? But okay, fine. So what is f of 1? What is k of 1? F of 1 is 4. K of 1 is 3. 4 plus 3 is 7, which you'd still get full credit if you left it as 4 plus 3. We basically never care about whether or not you simplify some simple algebra in this class. All right, I like this question. F of 4. So f of 4, here's 4. F of 4 is negative 3, okay? So what we just figured out from the graph is that f of 4 is equal to negative 3, okay? So right here, where it says f of 4, that's actually the number negative 3. So this computation is f, sorry, maybe I should have said, this f here is the f I'm going to write, boom. And then instead of negative 4 on the inside, we put down the number that it is, negative 3. So we're really interested in f of negative 3. So I come over here, negative 3, I go and hit this, it's negative 2. Okay. So the answer is negative 2. All right, same idea here. We're just mixing functions. So f of positive 3 is negative 4. Okay. This expression right here, f of positive 3 was negative 4. So the question as a whole is asking for k of negative 4. So let's find out what that is. That's up here. Negative 2. Okay, that's negative 2. This didn't really typeset very well. You can see a very faint horizontal there. This was supposed to say negative 1. This is k inverse. And, all right, the answer is going to be 1. Let's see why that's the case. So remember, k goes this way. K inverse goes this way. So k inverse of 1 is saying take 1 and go this way and then come back. So in other words, right here is -1, and then k of -1 is back to 1, okay? So these are inverses, and if you do one right after the other, it's as if you did nothing at all. Whatever you started with is what you finish with, okay? And that's true. So for example, if I write this, k of 3, the answer is 3. If I write this, k inverse of, let's say, 3, the answer is 3. Okay, but maybe I'm making that more confusing because this one is doing this, whereas this one here is doing this. So let me change this one, and maybe I could write it as k of k inverse of -2. Great, so that's -2. So now since k inverse happened first, we went here, and then k brought us back. All right, whatever. So that was just one, and we've already done this one. I just happened to erase it. All right, so this is the first page from the sample midterm that's been up online since Canvas was created. And I'm trying to let you know, like, okay, here are the things that Jeff is kind of hinting at on the sample midterm, like, hey, this is what we should be getting from chapter 1. And notice that a big topic is average rate of change. And then, can you evaluate functions? Can you compose functions? All of these are function composition, okay? So we'll spend more time with inverses a little bit later, but for now, there's that stuff. All right, now average rate of change, it might seem silly, right? Remember when we do these like trips here, and why would you ever care about this type of slope? And it turns out this is what you sort of normally do when like you compute your average speed, for example. So suppose that you drive to Denver, and it's a total of 62 miles. So let's see, 10, 20, 30, 40, 50, 60, and that little blip there will be 62. But so we have 60 and 50 and 40 and 30 and 20 and 10, and these are all in miles. Great. All right, so suppose you drive to Denver, a total of 62 miles, and it takes you 55 minutes. Okay, 10, 20, 30, 40, 50, right here is 55. And so there's 50, and here's 10. Okay, great. What is your average speed? Well, gosh, let's see, 62 miles divided by 55/60ths of an hour, and you get something like, I think it's 67 miles per hour. Yeah, so it's a little different, but whatever. Okay, and now, were you ever actually traveling? So were you actually traveling this speed your whole trip? Oh, sorry, your whole trip. No, you weren't traveling that speed your whole trip, right? You had to get in your car, and maybe you get on Mulberry, and you're doing 35 to 55, depending where you're at, and there's some stop signs, and then you get on I-25, and maybe if you don't hit traffic at all the entire drive, then maybe you did that, but in reality, this is your average, and you were going slower when you were in town, and probably slower when you get to your destination. You're not just going to like drift in at 67 miles an hour and parallel park and be good in Denver. So you were probably doing like 75 or 80 on I-25. So no, you weren't doing that your whole trip. Okay. Were you ever actually traveling that speed? We'll come back to that question. Okay, on the graph below, graph your distance versus time graph, what it might actually look like. So there's not one correct answer, but the idea is you start, and this is time, and this is your distance. And if you don't go too fast, then, how long does it take you to get on I-25 from your place? Is it 10 minutes a good estimate? So maybe by the time you get 10 minutes, you're at I-25. And how far away is that? For me, maybe it's like 4 miles. So in 10 minutes, I've traveled 4 miles. What does my curve look like to get there? Like, I could just do this, and that's me assuming I have a pretty constant pace. But the reality is, like, I'm going to come to stops. So, gosh, okay, maybe I do something like this, and I come to a stop, and then I go back, and then I hit it, Who knows how it actually looks? And the point is, we don't care. But whatever. So now maybe I'm on I-25, and now I'm going to be cooking and booking. I'm going to be doing 85 and breaking the law. And, okay, maybe I do that until about 50 minutes or so. And that gets me the majority of the way. And so I kind of take off, and hit some traffic and take off, and there we are, okay? Now I get to the final 2 miles. I'm exiting the freeway. So now I slow down and I kind of creep along, and then maybe like I come to a stop, okay? Maybe this is what my trip looks like in terms of how far I've traveled and how much time has gone by. So, okay, fine. Notice the average rate of change from start to finish. Well, so here's my function. This is f of t, okay? Or I could say d of t, my distance as a function of time. And my distance at 0 minutes is 0 miles, whereas my distance at 55 minutes is 62 miles. And so my average rate of change is 62 minus 0 divided by, and then I could say 55 minus 0, but this would be miles per minute. So I'm actually going to divide all of this by 60. Everything's over 60. Everything's over 60. And I'm going to measure time in hours. So now this is 55 over 60. And notice this is my average speed. That's exactly what we computed before. An average rate of change is often something we care about in life. We don't really care how you get from point A to point B. We just care that you got from point A to point B. And so what was happening on average, you know? Okay. So now let's go back to, were you ever traveling this speed? And the answer is yes. Okay, there had to be moments in time where you travel your average speed. So let's think about that. So is it possible? Now look, you had to leave your house, and it's not like you got in your car and instantly were traveling faster than 67. So you definitely started out traveling slower than 67 miles an hour, okay? Now, if you never hit this speed, if you never touch it, then that means your entire trip, you went less than that speed. But that's impossible, right? Because if you always go less than this speed, then you cannot cover the correct amount of miles in the correct amount of time. It can't happen. You're going too slow. So the reality is you had to go this fast at some point in time, even if it was just like, oh, right there you nicked it, and then you're going faster and then slower. Oh, right there you nicked it again, you're going faster, and you know. So there are moments in time where you do travel that fast. Okay. All right, cool, whatever. So average rate of change is not actually too big of a deal, but slope is a big deal in calculus. And average rate of change is our first sort of example of making sense of some slopes. There is a special type of average rate of change that we will look at a lot in this class. And I'm going to introduce it in a weird way, but bear with me. So first off, there we go. If we look at this computation here, then this computation is the average rate of change from x to x plus 1, okay, which is a little different than what we saw before. We're used to seeing numbers, you know, 2.5 and 3. Oh, that's a negative 2.5. All right, well, whatever. Whereas here we have variables, and so what the heck is this saying? This is essentially saying, like, what's your average rate of change from, like, your position to one x value into the future. So, for example, from x equals 0 to x equals 1, you're going from here to here. Your average rate of change is that slope, okay? So, anyway, let's look at a general quadratic function, and let's compute what this slope from where you are to one step into the future, what that would look like, okay? And if I'm using weird words, I'm just trying to say where you are, that's x. And then one step in the future is x plus 1. So this could be like a 2, and this could be a 3, or this could be a 0, and this could be a 1. It doesn't matter what this is, it's a pi, but this has to be exactly one more, pi plus 1, right? So I just say one value into the future. I don't know what to call it, but like whatever your x value is, you take a step over that has a size 1, and there's going to be some change in y, right? Okay, all right. So really, this exercise, at least right now, is an exercise in being able to make sense of this super abstract looking formula, which maybe we're uncomfortable with. Okay, so let's make sense of it. So, all right, here's the function f of x. So the expression f of, and then we have x plus 1. Well, look, what f does to an input is expressed over here. So it will square the input, it'll multiply that by a, then it'll add to it, and it'll do the input times b, and it'll add to it c. So in our case, this is a times, and now our input is x plus 1. And we need to square it, plus b times, and our input is x plus 1, and plus c. Great. So the computation, well, let's actually work this out a little bit. So what is x plus 1 squared? Well, that means x plus 1 times x plus 1. That's what it means to square something. You multiply by itself. And in case you've never seen this, I'll just also show you. If this whole distance was x plus 1, then to square it means we're going to form a square. So like maybe this length here is x, and then this length here is 1, right? Which means this length here is x, and this length here is 1. And notice that the total area, you get an x squared. Here you get an x times a 1, so that's plus x. And here you get an x times a 1, so that's plus another x. And here, this is a little 1 by 1 square, so that's plus a 1. So in other words, you get x squared plus 2x plus 1. You could have done foiling. There's many different ways to explain it, but whatever. That's what x plus 1 squared is. So I'm going to rewrite f of x plus 1 one more time. This is a times x squared plus 2x plus 1 plus bx plus b plus c. So what did I do? I just expanded everything. This b hit both x and 1, and that's why there's a bx, and that's why there's a plus b when it hits the 1. This a, I need to distribute. So you know what? Since I have an eraser and a pen, let's go ahead and just do that really quick. So I have an a, and I need to move this over. I should move this over too. Let's bring this back a little bit. Great. I have an a, and I have an a. Great. All right. So now I have distributed the a. I've expanded all this. Distributed b. Sweet. Here we are. So our numerator is f of x plus 1 minus f of x. F of x plus 1 is this monster. F of x is this monster. I have to do this minus that. That's what the numerator is saying to do. It's saying f of x plus 1 minus f of x. Okay, so let's do it. So I have ax squared minus ax squared. Okay, those are gone. I have 2ax. All right, that thing lives on. So let me just write this down. So I have 2ax. All right, I have an a. That lives on. In fact, I'll just circle everything that lives on. And I have a b. That lives on. Now bx, that cancels there, and c, that cancels there. Okay, so there's my numerator. And my denominator is x plus 1 minus x, better known as 1. Okay? So this whole big, nasty, disgusting expression is just 2ax plus a plus b. Okay, now something is happening here, but for now, I'm just going to let this exercise be weird and mysterious and gross, and we don't like it. That's fine, okay? You could just think of it as practice making sense of an expression like this. Expressions like this are very common in calculus, so I'm just exposing you now, okay? This is much faster than you typically get exposed to in the class, but I'm not grading you on it. I just need you to start seeing it, okay? All right, let's do something with actual numbers so that we feel more comfortable, okay? So let's fill in this table below. How the table works is each row is specifying your x value. So this is the row where everywhere you see x, you get to replace it with 0. So what goes in this box is f of 0 because what goes in this column is f of x. And then, well, what do you mean f of x? Well, you have to replace x with whatever the x value is, right? So this is 0 squared, this is just 0. What goes here is f of 1, this is 1 squared, this is just 1. So here's f of 2, this is 2 squared, this is 4, and then 9, and then 16, and this is f of 4, and this is f of 3, right? So the rows tell us the x value, and the columns are telling us what to do with that x value. Same idea here. And notice this expression. This expression is the same as this highlighted expression, right? I just simplified the denominator. I did x minus x, so I got 1. So here we are. Okay. So what do we do? Well, the row tells us the x value. In this row, my x value is 0. So everywhere I see an x in this expression, I'm going to replace it with 0. So this expression is saying f of 0 plus 1 minus f of 0 divided by 1. Now, going forward, I think division by 1 is a little silly. It's just going to take up a lot of space in our table. So I would like to just ignore that and just pretend we're looking at this, okay? So what is this saying? Well, kind of like please excuse my dear Aunt Sally, we do parentheses first. So 0 plus 1 is 1. And so what this is saying is, hey, can you tell me what's f of 1 minus f of 0? Well, conveniently, in this column over here, we see f of 1 is 1, f of 0 is 0. This computation is 1 minus 0. Okay, so it's 1. All right, and let's keep perspective here. So draw the slopes on the graph. This value is a slope. It's a change in y over change in x. It's an average rate of change. It was drawn in orange over here. And so it turns out the slope of this line segment is 1, okay? And, you know, each of the segments we're going to draw, the change in x is going to be 1. I'm going to go from 0 to 1, then I'm going to go from 1 to 2, then I'm going to go from 2 to 3, and so on and so on. Okay? So the next value that we should get had better be the slope going from 1 to 2. So that's this baddie. And boop, can I almost maybe, I'll take it, that's fine. Okay. And okay, so that's going to turn out to have slope 3, but let's go and just do it really quick. So let's make sense of this formula for this box here, right? What have I said to do? Everywhere you see an x, you replace it with the x value for that row. Here my x value is 1, right? Okay, so this is f of 1 plus 1 minus f of 1. That's what I care about. All right, so what's that? That's f of 2, right? Do that, minus f of 1. Okay, now we're ready to use our function. So what is f of 2? F of 2 is 2 squared, so that's 4. Minus, what's f of 1? It's 1 squared, that's 1. So we get 3. And yes, that's exactly the slope we were supposed to get for that, right? Okay, let's do another one. So now we're at the row where the x value is 2. So our formula is f of 2 plus 1 minus f of 2. And that's better known as f of 3 minus f of 2. And that's better known as 9 minus 4. So 9 minus 4 is 5. And so it turns out that over here, going from 2 to 3, that has slope 5. Okay. And we can continue this. We'll do purple. So maybe you see the pattern by now. And so since this is x equals 3, the first input is 1 more than 3, so 4. And we're going to do f of 4 minus f of 3. This is 16 minus 9. You get 7. Okay? So it turns out this slope going from there to there is 7. Okay. Boop. Great. So I slope 7. Lenny, I know. It's okay. All right. So now I get to hop back and tell you why I had us do the last exercise. Okay? Now, Lenny, buddy, come here. Come here. Thank you. Okay. So you probably saw a pattern with these numbers, right? And you can probably guess the next number is 9, and you would be correct, all right? Now, this function over here was a relatively nice function, okay? I could have had us do another table where instead of x squared, maybe I have us do 3x squared minus 17x plus 4, right? Ugh, could you imagine having to fill out all these values? Right? By the time we get to 4, I have to do 3 times 16 minus 17 times 4 plus 4. God, I would hate to plug 4 into this. That sucks, right? Okay, and then, oh my goodness, when we get here, we have to do all these computations, blah, blah, blah. Oh, this sucks. Oh, but wait a second. See, the reason for this exercise is to try and show you why sometimes in math, we just leave things unspecified, okay? So, in fact, I actually regret not making this function more challenging. So maybe I should have had it, something like this. And I'll do that on a future worksheet. But for now, this function here is 1 times x squared plus 0 times x plus 0, right? And all I'm doing is putting this function into this form. So what was called A is 1. What was called B is 0. What was called C is also 0. Now, this computation, which is the same as this computation, is right here. It's just this formula. And in our case, A was 1, B was 0, and C was 0. So I could plug in 1 for A, and I can plug in 0 for B. And if you do that, then all we're supposed to do in this column was actually input 2x plus 1, right? I'm plugging in 1 for A and 0 for B. So that'll give me here. And if I do that, well, now look, if x is 0 and you plug it in, 2 times 0 plus 1, 1. If x is 1 and you plug it in, 2 times 1 plus 1, 3. If x is 2 and you plug it in, 4 plus 1, 5. So by having a general formula, we can figure out exactly what we have to do with, very little work or less work, okay, for figuring out these slopes. And you think, okay, fine, sure, weird math factor, why do I care? Well, it turns out that we're going to care a lot about going between a slope and a function. That's like a big deal in calculus. So there's that. Like I said earlier, expressions like this, they're also really common in calculus, so I want to get us comfortable with it. And there's one other little takeaway that I'm giving us a sneak preview of. So there's something called a power rule, okay? And it turns out that when you have a function that looks like some number times x to some power, then its slope, so here's my original function, the slope is going to look kind of like this power is going to come down, I'll have n times, and this number just sort of comes along for the ride, and then I'll have x to a 1 less power, okay? The slope is going to kind of have this type of behavior, and that's called a power rule. And we can see, let me erase and clean up a little bit, sorry. So, going from here to here, this 2 came down, I have 2ax to the 1. And you can see that behaves like this, where this coefficient in front was a. Maybe I should just call this a, sorry. Okay, so my power was 2, and my 2 came down, and now I have 2a, and 2 minus 1 is 1. So this is sort of showing us a power rule phenomena. And in fact, we can see that again. If my function was a line, and now we do the same idea, and we compute this slope, let's get practice with it. So f of x plus 1 minus f of x divided by 1. This is what we need to do. Okay, so what's f of x plus 1? Well, here we are, and everywhere we see an x, we replace it with x plus 1 in parentheses. So that is f of x plus 1 minus, and what's f of x? Well, it's mx plus b. Okay, division by 1, who cares? All right, so now if we distribute this m, bop, bop, we'll have mx plus m plus b minus mx minus b. Distribute that, right? Mx is die, b's die, and we get m, right? Well, what do you know? The slope of a line that looks like mx plus b is m, okay? But this is also the power rule. This is also the power rule. Look, I have mx to the 1. What does the power rule say? If I want to figure out the slope, well, this 1 comes down, 1 times m times x to the, and then what goes here is 1 minus 1, and that's 0. Wait a second, x to the 0, this is just m, because that's a 1, right? So we can start to see some phenomena occurring that we're going to see again later on in this class. And so I want to show you that. I want us to have practice with slope formula. I want us to have practice with making sense of expressions like this, and specifically that part, okay? So, all right, now we're gonna take a slight pivot. We're still gonna care about average rate of change, but we're gonna start looking at the exponential function. So an exponential function is something of this form. And when people say exponential growth, people often misuse that phrase to mean the graph slopes up, but that is not what exponential growth means, okay? And we'll see that exponential growth, it's defined more so using the idea of average rate of change and the idea of proportional to. Okay, this was a vocabulary word from the last worksheet. It's from, I think, section 1.4 in the textbook. It's from the linear stuff. Anyway, whatever. Let's jump into it. So, first off, I want you all to think about why this fact is true and how you would explain it, okay? So you can pause the video and think about that. Otherwise, I'm going to jump into what the typical explanation is, and I think most people just give an example, and they'll say something like, well, look, if I have 3 to the 5 times 3 to the 2, then this is saying 3 times 3 times 3 times 3 times 3, and there's sort of 5 of these. And then I have to multiply, that's what that's saying. And then this one is saying 3 times 3, and there's 2 of these. And so in total, you're going to multiply 3 7 times. Okay, fine. So if that makes sense, great. And if that makes sense, we could play around over here and try and figure out what power of 2 gives us 8. The answer is 3. What power of 2 gives us 2? The answer is 1. What power of 2 gives us 1/2? The answer is -1. Okay. All right. And I want us to sort of play with math all along. And so if maybe property C, or part C, feels a little uncomfortable, and I want us to go back to thinking about this example here, okay? And in fact, I'll continue to use something like this. So imagine if I have 3 to the 5 times 3 to something is equal to 3 to the 4, okay? And actually, these are pretty big powers, so maybe I'll just do something a little bit easier. 3 squared, okay? We can wrap our heads around this. This is 9 times something equals 3. Cool. All right. Well, I bet that you can figure out that this something should be 1/3, okay? And so then the real question is, how do we get from here to writing 1/3 as 3 to some power, okay? And you're probably comfortable with the fact that 3 is the same thing as 3 to the 1. So now let's use this property, right? So the number 1, this exponent right here, should be what you get when you do 2 plus question mark, right? When I take this exponent plus this exponent. So in other words, 2 plus question mark had better equal 1. And you can figure out, wait a second, question mark is -1. And so, okay, sure, I guess this has to be -1. All right, fine. Maybe that's not very enlightening. Another thing you could think about is, well, look, what if you had a bunch of 3s? 3 times 3 times 3 times 3, right? And in fact, the more 3s I have, the bigger this exponent is going to be, right? Okay, well, and then wait a second. What if I had a competition going on? What if I start dividing by some 3s? Divided by 3s. And the more I have here, the more I'm going to divide. But what would if I could cancel, right? Cancel, 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 cancel. What we're really doing is just checking the difference. How many are up top versus how many are on bottom? And I said the word difference. We're checking the difference. How many are on top minus how many are on bottom? That's a difference, right? And what if there were none on top? What if the top was just the number 1? So there's no 3s. Oh, but then what if there were 2 3s on bottom? Well, that's the same as 3 to the -2, which is 1/9, okay? I would encourage you to play with this a little bit until it feels comfortable, if this is not comfortable. And if you don't know how to play with it, then let's talk about it. and get to where you can sort of engage with the math a little bit more, provided that's what you would like to do, okay? This probably won't make a huge impact on your future in terms of this class, and I don't know what you're going to do in life, but it can help because exponential growth describes a lot of biological phenomena, okay? And so the more comfortable you are with the exponents, it can help. But that's for you to determine in your life. Okay. Let's use B and C to argue or explain why this happens. Here's the whole idea. Imagine I told you that x was 4 and y was 7. Okay, so I'm going to tell you that, and I'm going to ask you, okay, what is x times y? What is it? And I hope you're thinking 28. I hope you're thinking it's 4 times 7, right? So what's really going on here is equals means equals. And so when I say x times y, I'm multiplying these left-hand sides. That is as good as multiplying these right-hand sides, okay? So what I can do is I can multiply these left-hand sides, and let's also put down what we have. This is a 1, this is a negative 1. So I could say 2 to the 1 times 2 to the negative 1 had better equal, and now I can multiply these right-hand sides. 2 times a half, that's 1. Now I can use some rules of exponents. That's 2 to the 0, right? And really all that's going on with this phenomena is if you have a number and you divide it by itself, you get 1. Literally, that is what this is saying. It's saying a number divided by itself is 1, okay? But they just think of it as, well, if you have an a on top, that's a to the positive 1. If you have an a on bottom, that's a to the negative 1. And so they would cancel one another and you get 1, okay? Which brings me to another little talking point, which is instead of thinking that, like, you know, x to the n is x multiplied by itself n times, okay, just like how over here I multiplied 3 by itself 5 times. That's great. We can also generalize a little bit more, and I could say, actually, I'm going to put a number 1 in front. So it's how many times we multiply the number 1 by 3, okay? And by making that little slight change, now, if I talk about 3 to the 0, this is saying multiply 1 by 3 0 times. Okay, fine. 1, that's what you'd get. So there's a few different ways to think about this fact, and when I was first exposed to it, I thought it was weird. Anyway, so I just want to show you, like, hey, there's stuff I thought was weird and I had to make sense of, and here are ways I made sense of it, and hopefully you find some of that helpful. All right, similarly, right, I thought the fact that a 1/2 power was a square root, in fact, a 1 over n power on 2 is an nth root, and that's true of any number here. For example, the 3rd power on x is a cubed root of x, okay? And I used to think that was kind of weird, and I made myself play with this. And I thought, okay, well, what the heck is happening here, okay? So first off, why do I believe this is true? Well, it's because the power on 2 is 1, and 1/2 plus 1/2 is equal to 1. So, like, if I know nothing except for this rule here, then it seems plausible, right? Because I have 2 to the 1/2 times 2 to the 1/2 had better equal 2 to the 1/2 plus 1/2. This is 2 to the 1. This is 2. Okay. So it seems plausible, but that doesn't really, okay, does this really pin down, like, why is 2 to the 1/2 equal square root of 2? Well, you see, this, if we don't know it, let's do what we like to do in math, baby. Let's call it x. So I don't know you, and your name is x. And I don't know you, but you're the same object. So in fact, this is x times x is equal to 2. This equation is the same as the equation x squared is equal to 2. And now if I ask you, can you solve x squared equals 2? Now you're probably starting to think square root of 2, right? And now you just have to start to reason, like, well, why should this be positive square root of 2 and not negative square root of 2? And, I don't want to get lost in the weeds on this. So I'm going to stop there, and I hope that you found something interesting about this, maybe different ways of thinking. Maybe, there is a tool here that's going on in the background, which is when you don't know something, give it a name. Because maybe the way it looks is tricking us. It's making us overthink things. And so I'm just going to give it a name. I'm going to call it X. And then I can start to realize, wait a second, this is a relationship I've seen before. So then that means this is a thing I've seen before. All right, moving on. So that was all rules of exponent review. Exponential growth. Exponential growth is when the amount of new stuff is proportional to the amount of stuff. Okay, what? Okay, so here is what I'm calling new stuff. Okay, so for example, this could be like P at t plus 1 minus P at t. Okay, so some population at time t, the population right now, versus the population one step into the future, the population next year. Okay, so the population next year minus the population right now, that's the change in population. This triangle symbol, you should read that as change in. Okay, so the change in population, it's proportional to the amount of stuff. Okay, so amount of stuff, if I'm talking about population, the amount of stuff is this. So the change in population is proportional to the current population. The amount of new babies you can have is proportional to the amount of people you currently have. The amount of new bacteria you can have is proportional to the amount of bacteria you currently have. See what I'm saying? Okay, so what does proportional to mean? It means exactly this. It means there's a number where if you multiply that number with one of your things of interest, in this case the amount of stuff, you'll get the other thing of interest. Y equals mx. This is a proportional relationship. Y is proportional to x. And it's because there's some number m that'll bring you between the two when you multiply. Okay? This is section 1.4 in the text. It won't talk about exponential growth, but it'll talk about the word proportional to. This is a big deal. There's a reason why I've put it in both of my handouts so far. Okay, so if you haven't watched last video, find the part where you talk about proportional to. Maybe go into more detail, or check out the textbook, section 1.4. Okay, so to be exponentially growing means the amount of new stuff is proportional to the amount of current stuff. Okay? So, for example, we have 1,000 E. coli bacteria, and every minute we get 4% more. Percent, okay? Percent. Cent means 100. So, for every 100 bacteria, you're going to get 4 more. Okay, that's what this is saying. All right, if you start with 1,000 bacteria, and that's what this is saying. All right, so let's start to figure out how much bacteria we have at each point in time. So look, we begin with 1,000. 1 minute later, we will have 4% more, okay? So the way to figure this out, I'm going to give you the answer first, and then we'll talk about why. So 1 minute later, you will have 1,000 times 1.04. Okay, why is that? Well, there's the amount of bacteria you started with plus 4% of what you have more, right? Okay, so I know people nowadays, they prefer decimals to fractions. Break my heart. Okay, fine. So this is P of 1, okay? But now if I factor out the 1,000, this is 1,000 times, and here 1,000 is being multiplied by 1, and here 1,000 is multiplied by 0.04. And hey, 1 plus 0.04, that is 1.04. So P at 1, one step into the future, is the amount you started with plus an additional 4%. And so it's 1,000 times 1.04. Okay. Now, P at 2, it's going to be P at 1. So this number here, which it turns out is 1040, okay, but that doesn't matter. This is a number, and I could either write all of this or P at 1, right? They're saying the same thing. They're saying 1,040. So, all right, look, it's 1,040, but then it grows by 4%. So I take this number here, and I multiply it by 1.04. We're probably not used to thinking of writing stuff out like this, where, you know, here you go. Here's the answer, right? P at 2 is P at 1 times this. Okay, well, that's not so useful, so tell you what. Let's write out what P of 1 is. P of 1 is 1,000 times 1.04. This expression is P at 1. And I have to multiply it by 1.04. 0.04. Okay, this represents the new growth in order to get to P at 2, right? So wait a second, 1,000 times that, I could have just written that one as 1,000 times 1.04 squared. And then the exact same logic, we're going to get to 1,000 times 1.04 cubed. And then P at 4 is 1,000 times 1.04 to the fourth. Okay, what's growing in this formula? Where do you see the x or t value, you know, oh, it's in the exponent. Oh, it's almost like the phrase exponential growth is because the exponent is growing. But okay, whatever, I digress. Okay, let's figure out how much new stuff there is. So we've seen this notation before. It was that super frustrating thing from before. And remember, what you do is in your given row, this is telling you your t value. So we're going to replace t with that value. Okay. And then we're going to make sense of this expression. This is P at 1, which is here. And this is P at 0, which is here. And if you take their difference, I'm going to write this in a really silly way. So P at 1 is 1,000 times 1.04. And then P at 0 is 1,000. And if you take their difference, well, it sort of works out nicer if you factor out the 1,000. Here I have 1.04 minus, and then here I have 1. Right? Because I factor out the 1,000. If I distributed this back, I'd get back up here. And wait a second, 1.04 minus 1, that's just 1. Or no, that's just 0.04. 0.04. Okay. So wait a second. Let's make sense of this in words. Okay, so amount of new stuff. How much new bacteria do you get going from minute 0 to minute 1? You get 4% more. What does that mean? You get 4% of what you started with. So, okay, fine. If we did this again, and now I'm seeing what's going to make this handout tricky, and I'm going to have to catch this in class and edit it. This 1,000 here is P at 0. And to get to P at 1, you have 4% of what you started with. You have to add it on, right? All right, if we figure out our new change over here, this is going to be how much is at minute 2 minus how much is at minute 1, okay? If you work it out, well, look, let's just remember, like, what was minute 2? Minute 2 was the population at minute 1 times 1.04. That's how we get from here to here, right? We multiplied by another factor of 1.04. So instead of writing this, I'm going to write this. I have P at 1 times 1.04 minus P at 1. And now I'm going to factor out a P at 1. And I have 1.04 minus 1. So this is my population at time 1 times, well, I mean, it's 4% of my population time 1, but yeah, so times 0.04, okay? Which again makes sense because going from minute 1 to minute 2, we gain 4% of the population we had at time 1. Going from minute 0 to minute 1, we gain 4% of the population we have at time 0. And if you continue this, going from minute 2 to minute 3, what's the difference in population? How much did we gain going from 2 to 3? You gain 4% of what you started with. That's my population at times 2 times 0.04. Right? So that's how this whole column is going to behave. It's always going to be, what is this, right? In column 2, so this is telling us how much we have to gain to go from here to here, to go from here to here. And you always gain 4% of what you have. So in this row, I have my population at time 3. And if I gain 4%, then this is my gain. It's 4% of what I have, right? And that's what I have to add on to P3 in order to get P4. That's really what I'm trying to get at here. In fact, maybe what I should say, maybe an easier way to express this is, look, P at the next timestamp is P at the existing timestamp plus 4% more of your population, 0.04. Okay, if we don't like that, let me just write out some examples really quickly. I mean, really, all those examples are right here. So the population at time 3, if I, for example, move that over, the population at time 3 is the population at time 2 plus the growth part. You grew by 4%. Okay, so that's what this is saying. The population next year is the population this year plus our 4% of growth. That's all this is saying. Okay. All right, let me put this back in the form it was in. Minus equals. Okay, fine. So, all right, whether or not we suss this out, what we do here is saying you take, so this delta P, delta P, delta P, it's saying you take the value in this box and you divide it by the value in this box. And what you'll notice is that you always get 4%. Okay, you'll always get this 0.04, which is very clear because of how I wrote it. For example, right, this says, this says delta P is equal to 0.04 times P at 1. I really should call this delta P at 1 or something like that, you know. So P at 1 is, where to go? This number here. Well, whatever. Okay. All right, here's what I was expecting you all to do. See all this fancy factoring that I did over here where I'm writing stuff like this? I didn't think you'd actually do that. I figured what you would do for this box, for example, is you would say 40, okay? Because this box is 1040. 1040, it's 1040. So what is P at 1 minus P at 0? It's 1040 minus, 10, it's 40. So now what this column is telling you to do is it's saying take your delta P, that's this number, and divide it by your P at that time. So I divided by 1,000. 40 divided by 1,000, here we go, right? And if you did that, if you always took the number in this box divided by the number in this box, number in this box divided by the number in this box, you'll always get this number here, okay? And that is because delta P is proportional to P of T. It's because delta P, the new growth in population, is 4% of the current population, okay? So, look, I probably could have said this better, or I probably could have said it in a way that would make more sense to you, but if you think you see what I'm saying, what I'd like you to do is think about how it should have been said. How would you say it, okay? And how would you say it in a way that can try and get someone else to sort of feel like they're discovering it or seeing it, right? Okay, all right, so this fact, the fact that the new stuff is proportional to the existing stuff, is what it means to be exponentially growing or decaying, okay? If you're gaining new stuff, it's growth. If you're losing new stuff, it's decay. All right, so that's what it means to be an exponential growth. And now if we were to write out a formula, we should really look in this column here. And if you stare at it for a while, you'll realize that P of t is 1,000 times 1.04 to the t. Okay? So, cool. Exponential functions are the only functions whose change is proportional to the amount. That means they satisfy this, okay? Because that's what it means to be exponential, okay? One of the fundamental ideas in calculus is knowing how a function changes almost completely specifies the original function. Knowing that, this relationship is true, it turns out it's pretty easy to jump to this is our function, okay? The one thing that's missing is actually just knowing the number 1,000, okay? Someone has to tell us the initial population is 1,000, okay? But this idea of knowing how something changes, it can start to tell you what the function is. That's going to be a reoccurring theme in this class, but not till like chapter 3 or something like that, okay? But we can already start to see where because of something that's happening with this relationship of change, it's also, the function itself is intimately related to how it changes, okay? All right, so let's solidify this. So we're mainly going to look at exponential functions in this form. So previously I had this form, okay? And k is called the growth or decay rate. Depending on if k is positive, then it's growth. If it's negative, it's decay. Choose a non-zero value for k and choose a value for a and fill in the table below. So I just want you to do this for yourself. So for example, maybe I'm going to use k is equal to minus a half and a is equal to 1,000,000, okay? So P of t is equal to 1,000,000 times e to the negative 1/2 t, okay? Which I guess I'll write as negative t divided by 2, okay? So that was me choosing a k value and choosing an a value, and I go through and fill out this table, and I would figure out what this thing is here, okay? And I believe what you're going to get every single time is e to the k. So whatever e to the negative 1/2 is, that's what I would get in this. But I'm going to skip this and let you kind of work through it. And what should happen by the end of all this, so here's where I want to pick it up. How do k and b relate? b is e to the k. All right? So in the problem we did that I actually worked through up here, okay, we had 1,000, and then b was 1.04 to the t, okay? So 1.04, that's equal to e to some number, okay? And what is that number? K is the natural log of 1.04, okay? So whatever your calculator says that is what it is. And the way to go between the two is, so this is going to look a little silly, but b is the same thing as e to the natural log of b, okay? And so it turns out that this is what's often called k. So how do k and b relate? K is the natural log of b. This relationship and this relationship are the same relationship. It's just whether it's an exponential form or log form, okay? All right, let's get a sense of how this all works. So what does b to the x look like? What if b was between 0 and 1? So I would choose a number. I'm going to use a half, so b is 2. Or, sorry, 1/2 and 2 and stuff like that, and see how it all works. And, okay, so if we do part I, or part 1, then there are some, all right, qualitatively is how I want to sketch this graph, and I'm looking for some key features. Something special about the y-intercept. Okay, the y-intercept is when x is 0. So if I look at my function, what happens when x is 0? B to the 0, that's 1. Okay, and that's true no matter what b is, okay? In fact, you know what? Let's do part 3 first. Part 3 I'll do in blue, okay? B is equal to 1. We're going to graph the function 1 to the x. It looks like this. It's a straight line. Boop. Great. There we go. I did part 3, okay? All right, now let's jump back to part 1. So now I pick a b value between 0 and 1. Maybe it's that, okay? Now, so I'm picturing, maybe b is like a half, okay, or something like that. So we have to think about what happens if you have 1/2 to the x. And I want us to know that this gets smaller and smaller as x gets bigger and bigger, okay? So, all right, what are the other, we're looking at key takeaways. There was the y-intercept, so I've plotted that so far. Something special when x is 1. So what happens when x is 1? When, I messed up the y-intercept, I'm so sorry. I need to be more careful, right? The y-intercept is still 1, right? Because 1/2 to the 0 is still 1. But 1/2 to the 1 is 1/2. In fact, b to the 1 is b. So when you get to the x value of 1, that's when you'll see what your b value is. So if my b value was 1/2, I'd be here, okay? And then there's just the general shape. So now I can have some exponential growth, and it'll look something like, exponential growth, decay, whatever. So this was b less than 1. I'm going to graph b to the x. And so as x gets bigger and bigger, b to the x gets smaller and smaller. This is exponential decay. The reason I said growth is because if you move to the left, it looks like growth. Okay, now let's compare that to this case. So if b is bigger than 1, it's still true that b to the 0 is 1. So we're still going to go through this spot. And basically we just flip it around, and so now it'll kind of look like this. Whoop. Okay. So, right, this is b bigger than 1, b less than 1, and then b equal to 1. And if we play a Desmos animation where, like, say, you let b go from something close to 0, maybe 0.1, all the way up to 2, okay, then what you would see is a really steep thing like this that starts to become kind of less and less steep. Whoop, and eventually it'll kind of pop to this horizontal line, and then it'll be like less and less steep like this, and then more and more steep like this, and blah, 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 right? So this curve will morph into this curve, which will morph into this curve. This kind of unravels that way, and this kind of ravels up this way. So anyway, whatever, but they're going to stay fixed here. And that's because anything to the 0 is 1. All right. So understanding the general shape and behavior for different b values, we could instead do the same thing for different k values. So this case, remember, b, the natural log of b is equal to k, right? And so it turns out that this scenario is when k is negative. And this scenario is when k is positive. And if b equals 1, then k is 0. If b equals 1, then k is 0. Okay. And so the graph of e to the kx, it looks the same. It's just in purple now. This is, so if you had e to the kx in purple, k is negative. And similarly, if this was e to the kx, then k would be positive. And if this was e to the kx, then k is 0. You actually just have the number 1, right? Okay, so that's going between b and k some more. I'm getting used to that. Okay, so let's just run through everything that we've talked about here. So the average rate of change for a function over an interval is defined as the slope between the two endpoints, b minus a. All right, given a function, its one-step change is this. If this one-step change is proportional to the function, what can we conclude? We can conclude that that function is in fact an exponential function. Okay, it looks like that, or it looks like this. And the relationship between b and e to the k is that b is equal to e to the k, right? If you raise both sides to the x, then this is b to the x, and this is e to the kx. Okay, so that's all we're doing. All right, fine. And finally, this one is kind of the trickiest. So what's going on? If you know this, wait a second. Where have we seen that before? The amount of new stuff is 0.2 times the amount of current stuff. Oh, so no matter how much you have, the new stuff is 20% of it. So in fact, no matter how much you have, you're going to have the original amount plus 20% raised to some power. This is going to be exponential growth, and you begin with 30. Okay? So see, by knowing how f changes, we're able to know how it grows. And by knowing where to start, we know where to start. So knowing these two facts, we actually know f of x. Kind of wild, okay? All right, that's it for this video.